Okay, here is another second law problem, very similar to the last one. We're going to start, as always, by drawing a diagram. So I have a 30-kilogram weight. You can pretty much just draw a box for really any object that it's going to be. And it's being held up by a rope. And the first thing we want to do is establish all the forces on here. So anytime we're on a planet and there's gravity, there's always going to be a force of weight pulling it down. So to calculate the force of weight, we always take the mass of the object times the gravitational acceleration. So that's 30 kilograms times gravity on Earth, which we have rounded to 10 meters per second squared. So there's a weight, it is 300 newtons down. That is what is pulling this object to the ground. But I want to accelerate it upward at a rate of 1.5 meters per second squared. Now, if there is no rope, this object is just going to fall, and it's actually going to accelerate at 10 meters per second squared downward. That's what gravity normally does. So in order to get it to accelerate up, we're first going to have to counteract the gravity, and then we're going to need additional force to get it to accelerate upwards. So let's figure out what force we're going to need. We know that the force required to accelerate an object is equal to the mass times the acceleration. So the mass of this object is 30 kilograms times the acceleration, which is 1.5 meters per second squared. So 30 times 1.5 gives me 45 newtons. So I need a force of 45 newtons upward to get this to accelerate at the rate I want. In addition, this isn't just the force total, this is what we call the net force. I need overall 45 newtons up. So 45 newtons on the rope would not be sufficient, because if the rope's only pulling up 45, the weight is pulling it down by 300, so this is still going to fall. So I actually need additional force to overcome the weight. So first I need 300 newtons just to counteract the weight and keep it from falling. And then I'm going to need an additional 45 to get it to accelerate upward. So I'm actually going to need 345 newtons to get this to accelerate up at 1.5 meters per second squared. Because the net force now, 345 up, 300 down, is finally going to accelerate upward at the rate that I want.